Hello. Good evening, everybody. Lady Luck cast me last, so I'm going to try my best to give this the energy and pep, I guess 8 p.m. On a Wednesday night deserves. So the title of my talk today is called Novel View Reconstruction for Intravenous Procedures. It's quite a mouthful, not very clear, and I hope through my problem statement we really break this down. By the way, my name is... Apologies. By the way, my name is Aditya Nagachandra, but I go by Adi, and my mentor is Ms. Corral. So onto my quad chart. The primary topics that I think I'm addressing here is the fundamental applications of computer vision, but in a novel way to imaging for surgical intervention. We're not talking about MRI scans, we're not talking about trying to identify early onset of cancer or lymphoma or leukemia. I'm talking about 3D scene rendering for a very interesting case that you'll later see. I also wanted to include a dynamic feedback system. I thought just a vision or just an image with annotation or segmentation just doesn't make me excited to look at it and to get further detail. So I felt that was a necessary addition to existing vision systems. As for my research process, I thought problem finding, and someone Professor Kleinrock introduced to us, Professor Alan Kay, really nailed into us, was that students should be rewarded for finding appropriate problems to solve, not just look for good solutions to ones that exist. I also wanted to create a pipeline for novel scene generations. Once again, it gets clarified as the talks goes on, and some very exciting next steps in lieu with the Dyson design competition. Now, I'd like to introduce you to a dear friend of mine and someone I call Dr. Kaneko, but Dr. Naoki Kaneko is part of the Interventional Neuroradiology Department at Ronald Reagan Hospital, but he's a brain surgeon at the end of the day. That is what he is, regardless of his title. So the bread and butter of this man really is working on aneurysms and strokes. We're talking about high urgency, time-dependent situations. He's required by his contract to live within 20 minutes of the hospital so that within 30 minutes of receiving a phone call, day or night, he's able to be in the operating room if necessary. So time is really of the essence. A quick anatomy lesson before I dive into my project. Don't worry, I'm not going to quiz anyone on this. I'd simply like to identify and point out the internal jugular vein. It runs on the right-hand side of your neck where your jawbone meets your neck, and in fact, you can feel quite a predominant pulse. It's among 3 veins that are the most significant in your body that are considered access veins in the medical community. You have 2 that run down your thigh, called the femoral vein. You have 1 on top of your heart, called the vena cava, and the jugular vein, which is used for all cranial surgeries. So I had the chance to actually be in an operating room at Ronald Reagan, watching him operate on my good friend Bob here, in between the CT scan. And you can see that this is a very crowded room, and the main machine I'd like to point out is this CT scanner. On your right of Bob's head, you have an emitter, and on the left, you have an absorber. And within Bob's skull, you have these cavities of veins, which are simulated by the same thing. When you go to a dentist and they give you a mold to bite in to make a denture, that's what they use to simulate these cavities. And they simply act as a prosthetic jugular vein in Bob's head. So when you're working with an aneurysm, you have to get an accurate enough imaging of the site of the actual aneurysm. Where's the clot? Or if it's in the case of a stroke, where's the leakage? Where is the internal bleeding within the jugular vein? So for that, you have a few choices of imaging, but this becomes very clear quickly that CT imaging is the only reliable choice. Ultrasound is real time, but it's a planar projection. It's black and white. You get no volumetric information at all. While MRI is the most accurate volumetric information, it's too slow. If someone is having a rupture in their brain, you can't really send them into an MRI machine and tell them, hey, take your time, and we'll run a 20-minute scan on you to try and figure out where this is. So a $1 million CT scan machine in the operating room is truly your best friend. And to find out the exact point of the hemorrhage or the clot is we use something called subtraction CTA, or subtraction computational tomography angiography, which is done by taking a pre-scan, injecting an iron-based dye throughout your jugular vein, and then a post-scan. And by directly overlaying these images and subtracting the difference, you're left with the exact site of the leakage or of the blood vessel in question. But as you can see here, we'll come through a few problems. It's quite slow. It takes roughly 7 minutes to get this imaging, and you cannot do this in situ, in operation. You have to step outside the room, have a look at the monitor, and then go back with that intuition as a doctor and operate. You have a limited field of view. A CT scanner head can only move roughly 120 degrees. You don't have a full 3D reconstruction of the blood vessel, and it cannot be used, as previously mentioned, during the procedure. And there's also no feedback. You are simply at the mercy of a doctor's training, although trustworthy, is something that you cannot verify through something as rigorous as a computer algorithm. I'd like to now bring, I guess, your attention onto a dire fact that every second of receiving suboptimal levels of oxygen to your brain, you lose 50,000 neurons permanently. And we're talking about an average stroke patient requiring up to 4 hours to be stabilized. That is 1 billion neurons, something that will inevitably lead to motor deficiencies in the future. So once again, time is really your enemy. Now comes to the rescue computer vision. This is a very late development in reconstruction of novel scenes. And while called 4D Gaussian splatting, I think it's best explained by referring to this as a time-encoded scene representation or reconstruction. On your right, you can see the input video, and on your left, you see the input video. On the right, you see a novel view. You're able to generate quite a deep depth map and volumetric understanding of the image. And I thought, when I first read this paper in March, that I could use this to address this problem. So I modified the encoder architecture. I used 3D Gaussians that are based on the concentric space of, we're talking about blood vessels, specifically the jugular vein, so veins between 5 and 10 millimeters in diameter, and used something called a hex plane encoder, one that I will touch upon later in my timeline of research, to generate what are called Gaussian multi-headed point clouds. These are simply estimations of important spaces that, when splatted upon, you create a blood vessel. Now, splatting is actually an analogy. First of all, this algorithm is created by the Max Planck Institute. Splatting is the choice of word they use because they describe this process to be like a balloon dipped in paint, and you throw it against a wall. And through these splatting, you're considering the concentric shapes you can pull and rasterize from this. And this allows us a 6-degree freedom of the blood vessel in question. This is a rough timeline of my research. I once again want to point out the problem finding aspect. It took me a long time to drill into a problem I was passionate about, a problem I could throw the resources and time IRI affords, and I quickly realized the complexity of this. Initially, I looked at game development 3D scene renderings, such as 3D scene reconstruction. But these aren't robust. They're physics engines. They're not required to create something of medical grade accuracy. Then we looked at NERF, something called neural radiance fields, and 3DGS, 3D Gaussian splatting. 4D Gaussian splatting can simply be explained as the 3D version encoded in time. So you have a time-dependent reconstruction of an image. So my main prerogatives were to combine these architectures, something for our usage, train a model and its test cases, and to create a haptic feedback sensor, which adds in a dynamic layer to this imaging system. So for the haptic feedback system, it was inspired by what I think this diagram encapsulates really well. When Dr. Kaneko was operating, his eyes were very rarely on the field of what he's trying to do. Remember, he's trying to put a 3 millimeter titanium wire of the catheter into a 5 millimeter jugular vein and trying to sense the tiniest ounce of torque feedback, which resembles a clot or which resembles an outflow. While looking at an ultrasound reading, while looking at, well, Bob doesn't have vitals, but well, if it's a real patient, his vitals, while listening to the nurse, while listening to any other information. It is really a very noisy environment, and one that is, frankly speaking, hard to do. I mean, imagine trying to write on a whiteboard while completely looking away is hard enough while trying to insert a 3 millimeter wire into someone who needs stabilizing. Which is why I described or designed a very simple haptic feedback sensor. Through my model of the blood vessel, I'm able to sense when the catheter is grazing a blood vessel surface or has reached a clot with sufficient torque. And that will simply provide a haptic feedback, sort of as a trackpad on a MacBook. Furthermore, I'd like Dr. Kaneko and surgeons to have the ability to maneuver this volumetric creation on a monitor. They shouldn't rely on a mouse or on voice. So the top of this ring has a pressure-sensitive piezo plate, which allows you to, with your fingers, really maneuver around the volumetric surface, which allows you full flexibility of the blood vessel we have constructed. I'd like to thank two people this project simply could not go further than a dream or an idea about. Professor Arisaka from the Physics and Electrical Engineering Department, and a doctor and professor, Dr. Naoki Kaneko. I'd also like to thank Mr. Venki Harinarayan. I think it's an amazing thing undergraduates are given the opportunities we are, and to walk into the resource, the time. As a 19-year-old, I found my curiosity taking over more than not. And as the last speaker, I thought it'd be quite fitting to thank Professor Kleinrock for setting this initiative up and for allowing me the chance to really chase after my ambitions. So, thank you very much.
Got a question? Oh, questions. Yeah, sorry about that.
How do you validate your
network with
your
splat construction? Right. So the splat, the 40 Gaussian splatting is actually designed for really complex scenes. We're talking about trying to make a 3D reconstruction of this room from just a novel image or just from one shot. So to use it for just a blood vessel, which doesn't have much noise, you can see from the digital. You can see from this that it's highly contrasted and it's just one image. Its robustness is remarkably very high, although in the medical field, remarkably very high doesn't really pass. So I guess robustness is something always needing to be tested. Yeah. But from my preliminary results, it definitely resembled something realistic that I tested on a silicon mold, really, a silicon mold of a
So it was like how do you what is the golden case then like confirming the results of the splatting needs to be done?
As in the
do I do a 3D scan or what's the?
Oh, I see. The confirmation of the splatting, yes, we're using like a combination of an MRI, but an MRI is volumetric in a very different sense. It's hard to get this level of precision with an MRI. So there's actually an even more expensive CT scan, which allows a 360 reconstruction. This is about $10 to $15 million and cannot be added into operating rooms as easily as a computer vision algorithm. So yeah,
I can pay for that.
Maybe.
Yes. So I'm not sure I understood the haptic feedback portion of this.
Sure.
So the haptic feedback is based on, in effect, the simulation of where the physical object of the probe, we'll just say, is in relation to the simulated version and location of the vein, but might not, if there's any inaccuracy, might not actually correlate.
It is mostly a direct indicator of, so for example, you're trying to sense a blood clot on a 3mm titanium wire. It's very hard to really sense this torque as whether you've reached a wall, whether you've reached a vein turning or going down or going up, or you've actually reached the site of a clot or a leakage. So
I tried to do plumbing.
Yeah. Or again, this is plumbing just on a vastly different scale. Yeah, so.
But the question I think I'm asking is, do you have a static model that's done, or is it an updated model of whether or not that haptic feedback is actually touching something, or if it's just in the model it's touching
It is a simulation, if that is the answer. Yeah, so we're simulating the catheter moving, and the catheter has a tiny probe attached. It's just like an IR sensor related to the ring. So it's able to directly get like an accelerometer reading out. And then that is inputted into what you consider the 3D reconstruction.
So that needs to be actually super accurate, or you might be giving incorrect feedback.
Yes, yes, but again, because the splatting is very computational. Also, I forgot to mention very quickly. Sorry, it is very computationally efficient compared to any other AI-based algorithms or engines. We're talking about something that runs on a $300 consumer level GPU. You require nothing further. So, yeah, to answer your question, it's efficient. Thank you.